All right, let's start with Chapter 1, An Introduction to Chemistry. In this chapter, we're going to introduce chemistry and why we study it. Chemistry is the science of matter. And what is matter? Matter is any object that has mass and occupies space. And a lot of times we use the words mass and weight interchangeably. Just so anything that has any weight, you can feel the weight, and it takes up any space at all, counts as matter. Chemistry itself deals with the composition, structure, properties, reactions, and energetics of matter. Basically, how matter changes. If you want to get more specific, chemistry is a science of electrons. We watch how things gain electrons, how things lose electrons, how electrons of one chemical attack another chemical. If you don't understand what the electrons are doing in a chemical reaction, then you don't totally understand the chemical reaction. And so once a complete mechanism is understood in a chemical reaction, someone has a complete idea of exactly what the electrons are doing at every second of the reaction. So to break it down further, a better answer to this is chemistry is the science of electrons and what the electrons are doing. We don't really go into the protons and neutrons very much in this class. Chapter 5 will cover on it a little bit. But really, when you start splitting the nucleus, you're basically doing nuclear physics and not chemistry so much anymore. So chemists devise experiments, interpret data, and synthesize new substances. And that's a big one. Chemists synthesize new substances that have never been synthesized before. Chemical engineers, once someone has made a new substance that's useful and people want a lot of it, like a new pharmaceutical or a new cosmetic, a chemical engineer, they figure out how to build factories to make lots and lots and lots of something, because you might need 1,000 pounds a day, and then that takes a factory. Whereas chemists work small scale in a fume hood, making new things that have never been made before, and chemical engineers scale that up so that you can make a lot of it so that it's affordable and available for anyone who wants it. And chemists try to understand how and why chemical changes occur in nature and in the human body. And when you know what's happening microscopically, chemically, then you can understand what you're observing macroscopically, which is a big scale, anything you can see. All right, and here we have one molecule of water. And we will get back to water in chapter 13. A major important part of science is learning the scientific method, and this is an organized way to approach problems so that you can take a complex, gigantic problem, break it down into bite-sized chunks which are manageable, and then work through them. And this is one of the main reasons that scientists are hired in all sorts of industries. For example, big banks in New York hire a lot of physicists, not because they want any physics knowledge, but because once someone is an accomplished physicist, they understand very well how to tackle a problem, how to tackle a very big problem that may be very diffuse and hard to really even define, how to break it down and logically go work through it. And that comes from the scientific method. In the scientific method, we first collect the facts and data relevant to the question. You first need a question. And then we formulate a hypothesis. This is a tentative explanation of the data, which means guess. It's your best guess of what's happening. You have no proof, no evidence. It is what you believe is probably what's happening. Then we run experiments. An experiment is anything you do to test whether your hypothesis is correct or not. And then we modify the hypothesis, because the hypothesis must explain every single piece of scientific data. If there's one piece of data that is not being accounted for by the evidence, then it's not a good hypothesis. A good hypothesis must explain literally every single piece of data that exists. Once all the evidence does support a hypothesis, it can become a theory. And it's important to remember that a theory is always in motion. It's always being rewritten. No theory is written in stone. A theory is our best guess, or not really guess, but our best current explanation of natural phenomenon, which is supported by a lot of scientific evidence. But that does not mean that it's absolutely correct. In the future, if new evidence is discovered, then theories are rewritten. And so 50 years from now, there'll be new theories that aren't in these textbooks or in any scientific textbook or PowerPoints or lecture because they haven't yet been discovered. So all theories are open to being rewritten later. And that's an important part of science because then everyone understands that a theory always has to account for all of the evidence, and that includes in the future. So if something 10 years from now is discovered and it doesn't support the theory, then you need to update your theory. Sometimes it's a minor update, sometimes it's a major update, like when classical physics gave way to quantum mechanics. So a theory is our current best explanation of natural phenomenon, but again, it's always open to revision if there's evidence in the future. Now, a scientific law is totally different. That's just a statement of what happens every single time. If you take a piece of paper, wad it up, throw it in the air, it comes back down. You can do that 10,000 times, it will come back down 10,000 times. Gravity is a law. Now, a law is not an explanation. A theory tries to explain why something is happening. A law does not. It just says what happens with no exceptions. A scientific law is what happens literally every single time with no exceptions. There is no good theory of why gravity exists. No one can really explain why gravity exists. It's not really well understood how it actually is related to the other three major forces of the universe, like the nuclear strong force, the nuclear weak force, or the electromagnetic force. And anti-gravity hasn't yet been discovered. You'll notice if you have magnets, in one conformation they attract each other, but in the other conformation they repel each other. And that's also true of the two nuclear forces. There's attractive and repulsive parts of it. But gravity is always attractive, and so that has not yet been explained. But again, a law doesn't require explanation. We have a law of gravity because it works every time. And so that's all you need for a scientific law is a simple statement of natural phenomenon where there are no known exceptions, and then it's a scientific law. As you can imagine, very few things happen every single time. There are very few scientific laws. The natural phenomenon part is important too. Science does not deal with supernatural phenomenon. It has no opinion. It has no opinion on ghosts or any other supernatural phenomenon. To be studied scientifically, something must be isolatable. You have to be able to isolate it, run your experiment on it, and that experiment has to be reproducible. So if you publish a scientific paper, someone else has to be able to read your paper, do exactly what you did, and get the exact same results you got. And if that's not possible, it's not good science. And so again, science has no opinion on supernatural phenomenon. All it states is that you can't study those things with the scientific scope and scientific tools because they're not things that can be isolated and reproduced at will. And so science doesn't deal with them. And that is the first part of Chapter 1.